long as I know the function f of x, y is given. Maybe it's x squared plus y squared plus 5 or something like that, right? But to calculate f, you have to know the value of x, which in our case is x naught. We know that number. And you have to know the value of y at x naught. That's given by the data, right? Y of x naught is a. So by calculating the given function f with the arguments x naught and a, you get the second term in the Taylor series. Right? So I got that. Okay. What about the second derivative? Okay. Well, you do that by differentiating this. Okay. See, once this gives dy dx, it also gives a higher derivative. Let's differentiate that, and I find that the second derivative of y with respect to x. Okay. And this comes out now with your multivariable calculus. What is it? Y is a function of x. So it's partial f, partial x, plus partial x, partial y, dy dx. Okay? I have to evaluate the second derivative at the point x0. Do I have all the numbers to do that? I need partial f, partial x. Again, I can't write it down because I didn't give you a specific f. But if f is given as a function of x and y, you can crank out partial f, partial x. It's a function of x and y. So plug in the initial data. X equals x naught, y equals a. So you know this guy. Okay? Okay. Same thing for partial f, partial y. If f of x, y, I don't care how complicated it is, it's a function of x and y, you can do the partial derivative, and this will be some function of x and y. Can you calculate numerically? Yes, because you know the value of x, which is x naught, and you know the value of y, which is a. So you know this guy. And what about dy dx at the point? We just did that. That's nothing. Okay? So now you get this term in the Taylor series. I don't have to go on. You can calculate the third derivative, fourth derivative of that. Okay? So what's interesting is that by using a numerical approach, we also see that to solve the equation, even though this is not very practical, if you had a first order equation and I gave you the value of y at a certain point, I could crank out all the other derivatives and get the Taylor series expansion. And you can do the same thing for a second order equation. If you had a second order differential equation, you would be given, this would be now second derivative with respect to x is f of x, y. Y of x naught would be given, let's say big A again, and y prime of x naught would be given, big B. And then the initial data gives you the first two terms in the Taylor series, and you get the others by differentiating it again. Okay? So it's just another way, this is not in the book, which I think is nice, that you can see even from a numerical perspective, you just want to just get a number and not get an analytical solution, you still come up against this issue of how much initial data do you need in order to march the solution forward. Okay, we'll just do this example and we'll pull it quick for today. Back again to like verifying solutions. And then what I'll do is I'll email people if there's homework or not, okay? I have to just look at it and see how far we went with homework assignment involved. Okay, let's look at the equation. Second derivative of x with respect to time plus 16x is equal to 0. Okay? That could be, for example, a simple oscillator, right? It's still about the same. X equals 0, or the pendulum that I had before, except now it's not theta, it's x, right? Okay. And I want to solve that equation, and how many initial conditions do I need to get a unique solution? It's a second order equation, so I need two pieces of data, right? So I'm going to tell you that x at pi over 2 has the value of negative 2. And I'm going to tell you that dx dt at pi over 2, so it's initial value problem, right? Remember, it doesn't always have to be equal to 0. What makes this initial value problem is I'm giving the initial data. It's called initial data. That comes from mechanics. It's always t equals 0. I'm giving the data, let's say, at t equals pi over 2. X at pi over 2 is given, has negative 2. And the derivative at pi over 2 is equal to 1. Okay?
We consider this a pendulum.
Yeah, it's a pendulum. It'd be a pendulum, a linearized pendulum, right? Exactly. With the G over L, I guess, would be 16 and some crazy units. Okay. Okay. The general solution, again, I don't expect you to know this at this time. We're going to derive this next week. Okay. The general solution, just have it so I get the constants, is C1 cosine 4t plus C sub 2 sine 4t. Okay? This is what the easiest way to do that is first show that cos 4t is a solution and then sine 4t is a solution. Then because it's linear, superposition holds, and therefore it's going to be valid for that linear combination. I'll leave that to you as an exercise, okay? Just show the solution. say 20. And then you should be able to verify. Okay. Now let's just plug in the initial data, okay, to get the values of C1 and C2. So this is like, it's the same type of we did before, except now there are two constants. Okay? Well, we're told that the value of x is pi over 2. If I go in this equation and evaluate pi over 2, I get C1 times the cosine of 2 pi, which is 1. And of course, the sine of 2 pi is equal to 0. So many times we get simultaneous equations, things in the homework where here the numbers were chosen so that one of the things go to 0, but that's not always going to happen. So I know x to pi over 2, so that equals -2. Okay? So C1 is known. Now, in order to get the other constant C2, hopefully if I do dx dt and evaluate pi over 2, set that equal to 1, I should be able to solve the C2. Well, let's get dx dt. Okay, dx dt is going to be minus 4c1 sine of 14. And again, I'm doing this rather quickly. If you're not following, you have to review your calculus, okay? You got to know the derivatives of sines and cosines, and also you have to know the chain rule, right? So, the derivative of cosine 4t is minus sine 4t and the 4 in there, right? Plus 4c2 cosine of 4t. And finally, let's evaluate dx dt at the given point, which is at pi over 2, right? Okay, I get a sine of 2 pi, which is 0 again, so I get 4c2, right? This cosine of 2 pi is equal to 1. And therefore, that has to equal 1. I'm told that dx dt at pi over 2 is equal to 1, so right away, c2 is equal to 1/4. So now that I have those two values, I can write the unique solution as c1, what do we find for that? -2